All right, so let's get started. Welcome to another installment of the MSPE Graduate Seminar. It's a true pleasure to introduce to you today's speaker, Dr. John McLennan, who's a professor in chemical engineering at the University of Utah. Dr. McLennan is a fellow Canuck, a Canadian. He earned his doctoral degree at the University of Toronto. And he is currently a co-principal investigator on the, I think, really exciting test site, the Utah Forge project. And I look forward to his presentation. All right, John.
Thanks, Rami. So I'm going to set this for 40 minutes. And it could wake us all up when it goes off. Okay, so it's a real pleasure to be here. I really like Tulsa as a city. I've lived here twice. I have had 2 kids that were born in this city. Of course, I can't remember anything about the city because that was so long ago, but it doesn't matter. What I want to talk to you about is something that's more recent, and this is this FORGE project. And FORGE is an acronym that stands for Frontier Observatory for Research in Geothermal Energy. And basically what we're doing in this is we're using hydraulic fractures to create an enhanced geothermal system. And I'll explain what that means as we go through the talk. Commonly when you get these from producing companies, you'll see fine print that's a disclaimer. We don't have a disclaimer, we have an acknowledgement. And the acknowledgement is that a great deal of money was provided by the federal government, the Department of Energy in the United States to fund this. And then this actually is important. This is saying that there's lots of people and lots of stakeholders at a local level that are relevant to your projects, whether they're oil and gas, geothermal, solar, wind, whatever. And those people matter. And what we particularly worry about in this situation is the potential for unintended seismicity. And that's why we interact constantly with the stakeholders, the people that live nearby, to keep them up to date on what is going on. And okay, so let's dive into it. Well, we all kind of have an idea of geothermal energy, right? We've seen these pictures of steam coming out of cooling towers and stuff like that. Usually those come from what are called hydrothermal geothermal applications, hydrothermal geothermal plants. And those geothermal plants tend to be in plate boundaries. You can see they're all around the ring of fire. Iceland, there's a rift that's pulling apart, and you can imagine why this is. Why is this? Because you've got hot rock that's close to the surface. Iceland, you got hot rock that's at the surface as the North Atlantic rift moves apart. Now that's a mixed blessing. Okay, it provides the heat, and it allows you to generate geothermal energy. But it has some consequences, because the consequences are it's only available in certain parts of the world. Much of, for example, the eastern United States does not have this luxury of the heat that's provided there. So the geothermal plants that conventionally you hear about, you read about, are what we call hydrothermal geothermal plants. And those plants need 3 things, okay? They need this heat close to the surface. They need some natural fracture for fluids to move through, and hey, they need in situ fluids that are moving. Okay, so hot temperatures, fluid, and fractures. And actually, this is a fracture from an operating geothermal plant called Steamboat outside of Reno, Nevada. And you can see from the scale that these are significant fractures. And so in these hydrothermal situations, most of these wells are drilled most of these wells are completed barefoot, large open hole sections. They just have to reach a fracture, and one or more fractures, and at least one of those fractures has to produce hot fluid. And so you can see what happens conceptually here is that you're producing the hot fluid, comes up to some sort of a power plant in the surface, and this power plant can operate in a number of ways. It can be a heat exchange system, a binary plant, organic Rankine cycle plant, where you have a heat exchange working fluid that you deal with, or you can flash it to steam. Nevertheless, fluid is re-injected back down for a recharge. It's kind of like voidage replacement in the petroleum industry, except we don't want our voidage replacement to happen quickly. We want it to happen over 10, 20 years so that the fluid can get back in and gradually move back towards the production zone and pick up temperature on the way. Now, as I said, these are common, and look at some of the characteristics of these systems, and you can understand why oil is so valuable. You know, the energy density of a barrel of oil, if you combust that, it's much, much higher than a barrel of water, okay? And that's why for these geothermal systems, to make them work, you need large amounts of fluid, and preferably fluid. The higher the temperature, the more efficient the electrification, conversion to electricity is. In these conventional hydro systems, the heat is transferred convectively, okay? And as we know, convection involves fluid movement. So think about this. This goes back to the fractures that I was talking about. That fracture convects up, that fluid convects up from great depths through a natural fracture system to a shallow enough depth where you can economically drill and access that particular fracture and produce that fluid. And so if you looked at a plot of temperature versus depth for a conductive geothermal reservoir, it's going to be linear. It's going to go straight like this. Whereas a convective temperature profile, temperature versus depth, is going to go like this, because you're convecting fluid rapidly from great depths up the fracture. So these conventional hydrothermal systems are convectively dominated. And that's because of extensive natural fracture systems, although you only produce out of a few alpha fractures. Now, Southern California, or Northern California, has the geysers, and that's the biggest geothermal operation in the world. And that's almost producing a gigawatt of power with multiple wells. To put it in this perspective, you might have an average well that will give you 6 megawatts of electricity. And the biggest wells, some of these wells in the geysers, you could be producing 50 megawatts of electricity. But to put that into perspective, it takes a lot of flow to get 50 megawatts. Let's look at it. See, at 200 degrees C, maybe a megawatt, and a megawatt might provide electricity for about 1,000 homes in the United States. And what's that? 360. So maybe nine barrels a minute could serve to produce 1 megawatt of power. So to produce 50 megawatts, you know, that's huge, unbelievably great well. Okay, so you say, well, this is okay, but that only provides heat, that only provides geothermal power in these parts of the country, these parts of the world that are near where there's a hot rock body that's relatively near the surface. You know, Indonesia, Japan, some places in Italy, California. But, you know, what happens if we access the heat differently, or if we create geothermal energy differently? Suppose we drill to temperature and provide the other two missing elements. Right? Remember the one thing we needed? We needed heat. Let's drill to the heat. Then let's artificially provide the fractures. Then let's artificially add the fluid into this system to create a heat exchange system that mimics a hydrothermal system. But the advantage is that we can drill in a larger part of the country. We just have to drill deep enough to get the temperature. So let's look at this map. So this is a geothermal map, or a heat map of the United States. And concentrate here. You can't read it. That's 150 C. So typically, an organic Rankine cycle power plant has break-even economics at about 150 C. That's what we used to say. Now, there are these plants that go down well below 100. And so it's sort of changing the game. But let's say that that's what we require for an economic power plant. So we can see that if we drill 10,000 feet, there's a bunch of real estate where this could possibly happen. We can at least drill to get to the temperature. Now suppose we have drilling technology that allows us to drill at an adequate price to 6 kilometers. That moves this 150-degree C pattern over a greater part of the country. And so what you've got there is, now with drilling technology, there's the potential to access heat at economically viable drilling temperatures. So you drill to the heat, you hydraulically fracture to connect 2 wells. Okay, I'm going to connect 2 wells, and then I can inject fluid in a closed loop where I pump fluid down one well. It travels through the hydraulic fractures, picks up heat, comes up the other well. We flash it the steam at the surface. No problem, eh? I mean, it's no problem, except we've been trying to do it for the last 50 years, okay? People, this is not a new idea. It first came about through the Los Alamos Scientific Lab at that time. And they had a project at Fenton Hill in what's called the Jemez Caldera. No, caldera, that means dormant volcano, okay? So you know it's hot. They still had to drill to about 11,000 feet to get, really hot temperatures. But they tried this at Fenton Hill, and for a number of reasons, it didn't work. And I'll show you one of the reasons on the subsequent slide. They tried it, this is a place in Wales, Rosemont. They tried it, a couple of places in Japan, just barely successful in Sault-Sous-Forêt in France, Germany, and $400 million failure in Australia. So it's not easy to do, but there are some things that are working in our favor now. And one of the things that's working in our favor is drilling technology. Okay, so now rather than drilling vertical wells, as these were subvertical or barely steered wells, you can drill wells that are inclined. And now you can imagine that if you know the direction of the minimum horizontal stress, you drill those wells in that direction, bang, 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 you can have, just like in an unconventional where you have multi-stage fracturing, you can have multiple fractures, and you can have a tremendous surface area for this heat transfer to occur in. So that was the Department of Energy's vision back in 2000 and I think it was 14, I can't exactly remember, but where they picked 5 sites in the United States. And they let everybody do a paper study. And that was to demonstrate feasibility of their location being a site for an enhanced geothermal systems laboratory. And so there were, I think there was one in California, one in Nevada, one in Idaho, ours in Utah, and one in Newberry Volcano in Oregon. Now, that went on for a year, and then the Department of Energy, they did what, and I learned the lingo now, they down selected. Okay, from 5, they down selected down to 2. And those were, Sandia National Labs had a well in Fallon, Nevada, or had a prospect in Fallon, Nevada, and we had a prospect in central Utah, near the city of Milford. And Fallon drilled a well, and we drilled a well, and you do sort of basic reservoir characterization. But what we're interested in here is we're interested in temperature, and we're interested in the potential for mitigating thermal depletion. We're looking for thermal reservoir characterization. And it turned out that ultimately our site had superior characteristics. So in 2009, so in 2017 we drilled a well here. 2019 we were awarded this, and the goal is to drill 2 deep wells and multiple monitoring wells. And this money has gone from $130 million to $220 million. And of that money, half goes to drilling and operations, and half is allocated to research organizations through DOE FOAS that are managed by the university to do geothermal research. Because we're going to drill these 2 wells, but we're only going to frack the toe of these wells. And so that leaves a huge amount of real estate along the lateral length for various people to try out field trials, hydraulic fracturing techniques, fiber optics techniques, sliding sleeves, various adapted for the geothermal business, and logging techniques, perforating, all sorts of interesting stuff. So this doesn't mean much, right? This is where the Ford site is in central Utah. There's nothing much that lives or grows here. It's high desert, and it's interesting. And the reason our congressional delegation in Utah likes it is because in addition to the Ford site, there are 3 other geothermal fields. There's a wind farm. There's 2 solar fields, and there's a biogas facility that converts hog manure to gas that they sell directly to Dominion Energy. Actually, you can see this is a little larger. Okay, so the Ford site is in here. There's the Blundell hydrothermal power plant there. It produces 35 megawatts of electricity. Cove Ford is operated by ENEL, which is an Italian company. And CERC is down here. It's operated by an American company. CERC maybe 15 megawatts. And so these are the 3 producing geothermal fields in Utah. But the difference is that across this fault, for whatever reason, for whatever hydrologic reason, these are convectively sourced geothermal reservoirs, okay? They got natural fractures and the fluid is coming up through natural fractures. Here, it's across this bounding fault and it's conductive. That the heat transfer is conductive and not convective from depths. So why did this site work? Well, you can see it's pretty lonely, right? There's not much out there. There's no endangered species. So it's just like an oil field, right? You have to do, it's federal land in the United States, so you have to do a NEPA review, and you're looking for endangered species, you're looking for nearby human activity. There's no farming here because the water is not potable. There is an aquifer, but the water can't be used for anything. It cannot be used for agriculture or drinking. And so it was pretty much an ideal location for selection of the forage site, which was based on 5 or 6 criteria. The first criteria is that you have to have an adequate temperature. And they picked the 350 degrees centigrade because it was borderline, okay? It was something where oil field technology could just barely make it, okay? And there's a huge opportunity for translation of technology, moving technology from the oil field to geothermal. But 300, I said 375, 350, you can certainly operate oil field tools, some tools up to that temperature. And they wanted that temperature to be reached at depths that weren't going to cost you too much to drill wells. Okay, 5,000 feet is shallow, so your cost of drilling would be moderate. Low permeability rock is granite. Okay, it's literally tombstone, and a low risk of indecisivity. This has been one of the biggest problems with enhanced geothermal systems up to the present time. There's been 2 classic examples at least, Basel in Switzerland and Pohang in Korea, where enhanced geothermal systems activated natural faults. And it's no different than what's happening in the Arbuckle Formation that you guys are all familiar with. I mean, you felt the earthquakes probably in this building. But understanding the geology, and this site is relatively aseismic. University of Utah has a seismograph station. We've been monitoring this part of the state for 40 years, and we have a very good handle on, and we think that the risk of induced seismicity is going to be low. Although all of our hydraulic fracturing operations, just like a conventional operations, have a traffic light system, that there are certain criteria. If you create a magnitude X earthquake, you have to shut down. If you create 10 earthquakes that are a little bit less magnitude than that, you shut down and you can potentially restart. A magnitude 3, I probably have to go work at McDonald's. The project, there'll be a lot of rethinking in it. Low environmental risks, of course, and no connection to a hydrothermal system. And so this well had all of this. And so here is the conceptual program for drilling this, setting this up. And this is for forage. So we'll drill the first well, and in fact we have drilled the first well. And this well was drilled at a 65-degree tangent, so 65 degrees from the vertical. It wasn't completely vertical. At first, we wanted to go horizontal, but we were talked out of it by advisors because at 65 degrees, we can wireline logging tools into the hole on bogies. Okay, I don't have a picture, but it's just like a 3-dimensional skateboard where you put the logging tools on this and it slides in. And indeed, we were able to get tools into measured depths of 11,000 feet. You drill the injection well. We're just going to do 3 fracs at the toe of the injection well. Okay, and I'll talk about those fracs later on. There's a 200-foot barefoot section in this well. We'll do a slick water frac in that. Then we'll come up the hole. We'll do a slick water casted perforated fracture, come up the hole further, and do a cross-linked fluid cased and perforated fracture. No sand, but we will create 3 fractures. And the goal here is just to establish a microseismic cloud. We have 3 wells that are drilled almost to reservoir depth, and each one of those wells will have 12 geophones in them. Plus there's an extensive network of geophones at the surface, and we'll be mapping seismicity in real time during the frac job. So after that, you take your production well and you drill that production well until it intersects the microseismic cloud. Now, everybody will say, hey, microseismicity, well, you don't have that much resolution. You don't know whether those are dry fractures. You don't know whether they're wet fractures. That meaning whether hydraulic fracturing fluid has gone into those fractures or just something out here where the reservoir is responding. And that's 100% true. And we don't know quite what to expect, but we just really don't have many other measurement systems. In a conceptual, conventional, commercial agenda, you'll have fractures all along the length of this hole, and you'll interconnect. And as I said earlier, the reason that we're leaving this open is because there are DOE contracts that will be issued for people to use this as a field laboratory and test out technologies. We've let 17 contracts so far for $40-odd million, and in about a year and a half, 2 years, there'll be another tranche of those contracts to look at various technologies. Okay, so let's go back to let's think about that. What I just described. We drill one well and then we frack. Well, why not drill both wells together? Well, the problem is that we don't exactly know where those fractures are going to go. I mean, we've been doing hydraulic fracturing since 1947, but as Ralph Beach, who's a famous Amoco hand who lived in Tulsa, Ralph was doing an SPE talk one time. It was in the late 90s. And he said, and he was doing a summary of hydraulic fracturing technology up to that time. And his famous quote is that we've gone on 50 years and we know everything about hydraulic fracturing except length, width, and height. Okay? And so, hey, and let me tell you, since Ralph gave his talk, we haven't improved substantially. Okay? So, we want to drill the first well first. And the real evidence for this came with this Los Alamos project that I talked about. Late 80s, okay? Or the early 80s, late 70s. In the Jemez caldera, and they were injecting into EE2 and trying to connect with EE3. And this was a big job at the time, right? This was 83. 50 barrels a minute, 5.6 million gallons of fluid, 200 mesh calcium carbonate for diverter. But there was no connection. It was established. Okay? They did not get connectivity, adequate connectivity. And this was really one of the big problems. And let's look at why. Okay, what I'm going to show you is a map of the microseismicity. And each one of the dots on this next slide is an indication where they found a microseismic event. And remember that when you break something, there's a release of energy. And that energy can be detected acoustically, or it can be converted to acoustic energy, or it travels through the formation as a mechanical pulse. And you can triangulate on where that energy came from. So you have a chronological indication of where your fractures grew. And so let's look at this. Okay, here is the microseismic map from the Los Alamos fracture in December 1983. So here's the production well. Here's the injection well. So they want to frack, and they want to go from here to here. So this is a plan view. So they were slightly inclined, and they were anticipating, sensibly enough, that the fractures would be traveling in this direction. All the microseismic activity was in this direction, and so it's just a lesson of human frailty that we're going to take the cowardly approach, and we're going to drill and frack, and then drill into the cloud and hope that we can have a connection. So where are we so far? As I said, we have 3 vertical wells. I'm not showing one here. I need to update this. There's a well that's drilled here to 9,500 feet. A well that's drilled here to 9,000 feet. Actually, that well was drilled to 9,000 feet after all. A vertical well that was drilled in 2017, and this well. And so you can see the trajectory of the horizontal well that we have drilled, sub-horizontal, 60-odd degrees. And so in each one of these other wells, we're going to put in geophones. 12 geophones down as deep as we can put them into the well. And so you're going to use these geophones to triangulate on those microseismic events so you can know where the fractures are growing, plus a surface array of geophone instrumentation. And you can see here that we have drilled this first well. We've drilled it in what we think is the direction of the minimum principal stress. So that we're hoping that here's the trajectory of the wells. We're hoping that the fractures are all going to go like this, and we'll find out soon enough. And so that well is being drilled. The monitoring wells are being drilled, and so upcoming we will be stimulating this. I'll talk about that a little bit later. Now, we've learned a bunch already, okay? And one thing that I've learned about the geothermal business is that they're even more reluctant to change than we have been in the oil patch, okay? And these wells, historically, they were drilling these geothermal wells with roller cone bits. And with those roller cone bits in that well that I said we drilled in 2017, we drilled that well with roller cone bits because that's what everybody was doing in the geothermal business. And we were drilling 8 to 10 feet per hour. And you know, that's just nowhere. And from those statistics, 50% of your cost for a geothermal plant comes from drilling alone. You know, in some of the hotter wells now, much more comes from casing because you've got exotic casing, you've got titanium and stuff like that. However, when we started drilling this inclined well, we said we're not going to use roller cones, and so we were using PDC bits, and we were experimenting, and we were having you know, some growing pains. We got into the curve and things acted well. The reason that we're having growing pains here is that we had a mechanical rotary steerable system. So a device that it mechanically operated, there's a pendulum in it, and if you went off vertical, the pendulum went down and it pushed you back to vertical. But the problem was it got gigantic pads on this device, and those pads were not transferring the load to the bit. The pads were allowing you to make the changes, but there was so much friction that the load was not getting to the bit. Now, when we got to the curve, we couldn't use that, and so hallelujah, things started to look a whole lot better. And so progressively through this, as we went through the curve and the tangent, we were working with the bit vendor on a daily basis and changing cutter design, cutter specs. We ran a lot of BHAs on this, and the accountants didn't like that, but it really made a tremendous difference. And since that time, we've gone to drill 2 other wells where we're now up to typically drilling 100 feet an hour and 2,000 foot bit runs. And so you know, these wells can be drilled, and it's dramatically changing. And that's one of the reasons people are starting to get excited about geothermal energy, is that they figure, hey, you know, they can actually drill these wells. You know, some of those wells in China, some of the ones that the China Geologic Survey has drilled, some of those wells are taking a year. I think if they go to PDC technology, those wells can be drilled dramatically faster, and it's going to make a big difference in what goes on here. The other thing that came out as a really nice research concept here is we work closely on this with Fred Dupriest and Sam Noyer. And those are guys that they're at another university. They're at Texas A&M. But Dupriest is the guy, when he was with Exxon for his career, that really adapted mechanical specific energy concepts and brought them to the drilling business. And so what this is, okay, mechanical energy, we can all kind of figure out what that is. We can look at, we've got 2 terms. We've got a weight on bit, okay? And that's how much energy is expended due to axial pressure on the rock face from the weight on bit. And then we've got 2 other terms that have torque on them, okay? So torque times some sort of an arm is going to give you a rotational energy. And specific, anytime you hear the term specific, you know you're normalizing by something. And so what they're normalizing by the volume drilled in a particular period of time. And so what this tells you is that if you minimize this number, then that's going to maximize the rate of penetration that you've got, okay? Because you are not expending a substantial amount of energy to the drilling process. The complication, of course, is how much is taken up by torque and drag, and separating that out from what happens at the bit face. But we use this religiously, and it really changed how things work in drilling these wells. Now, it's common in the oil patch these days, but this was just an obvious example of technology transfer. The other thing, okay, so we don't have much time to talk about anything here, but so I'll just high level talk about a few things, is that you have to do reservoir characterization in this. you have to be aware of natural fractures in these formations because, you know, this rock is granite, and probably a lot of the fracture growth is going to happen because you're inflating natural fractures when you're stimulating. So you need to know the natural fractures. So you have to log these wells. You know, I don't quite know what to do with a gamma rate in a granite. I mean, I know there's more uranium or less uranium. Resistivity, this rock is dry. I don't know what saturation I'm getting, but there are dipole sonic is particularly important because it gives you the mechanical properties of the reservoir. But the problem that you have with these wells is that we're starting to get up to 230 degrees centigrade, you know, and that's more than conventional logging tools can drill. Schlumberger has a cement bottom log tool that'll go to 500 Fahrenheit, but it's a very coarse tool. Their ultrasonic borehole imager, I think, goes to 300 Fahrenheit, and their FMI, formation micro imager, which looks at, you know, that's what I can use to find these fractures, goes to 350. And so this is all hotter than that. And you're in the well for a long period of time. So we found a great solution that Schlumberger provided, and that was their through-bit technology, where they have a bit with a hole in it, and you run tubing into the hole with that bit on the hole. And the good deal there is that you've got chillers on the rig. Okay? Even when you're drilling, okay, you have to be chilling your drilling water. We had 3 chillers and operating full time to keep the mud down to a temperature where the bits just weren't going to weren't going to fall apart. And so as you don't have this logging tool in it, you just have this, a tubing that you run in the hole with this on the end. And then after you get, and you can see you can be circulating, you can be cooling as you're going. And then after you get to the bottom logging depth, you pump the tool down. You know, just like how you would pump tools down in the horizontal wells, a little parachute on the end, and you just push it down, you pump it down. And it goes through the bit and it latches, okay? And so your logging tool goes through this bit and then it latches. There's some device in there that catches on to it. And you then disconnect your wire line. This is the only tense moment, okay, where you're watching the temperature build and build and build and build, but you're just sitting there because you have to wait and make sure that all the logs are going to read before you disconnect the wire line. So you disconnect the wire line, you pull that out of the hole, and then you log on the way out of the hole with this, and you record everything on memory. They're just fantastic. Really, really a cool solution that, you know, it's not necessarily quite as good as a full diameter FMI tool, but it's pretty good. And so we were able to log these granites. And I just wanted to give you a perspective on, are these granites different from the shales that you know we hear about so often? Yeah, indeed they are. Probably much higher modulus, okay, than the shales. Poisson's ratio, you know, who's to say what that means? UCS, you know, they're strong, but they're not strong. 25 to 30,000 psi. You know, you've got quartzites and some even hard limestones that may have higher unconfined compressive strengths than that, but they're still hard. This was very interesting, the friction angle. So think about your Mohr circles and your Mohr envelope when you're looking at wellbore stability. This has a very high Mohr envelope. So that means as I put confining pressure on the rock, as I go deeper, the strength builds very rapidly. And so drilling becomes progressively more and more difficult. And so you can just take from these things that these rocks are going to be hard to break, even if this is just compression. And this is fracture toughness. And the fracture toughness is probably significantly higher than conventional shales, okay? And fracture toughness is a proxy for tensile strength used to describe the ability for a fracture to propagate. So that's something you have to overcome to propagate a fracture. So I think the message here is that, you know, they're not that different from shales. You know, they maybe have a higher modulus, and you're gonna have narrower fractures that you create. But am I gonna create fractures? Probably not, because this number is high and this number is high, and your tensile strength is going to be high. It's going to be difficult to grow hydraulic fractures in virgin rock. You might be growing hydraulic fractures in virgin rock, but then they're going to find these natural fractures that we know exist in this reservoir, and they're going to follow that network of natural fractures. And this has a lot of implications, and if we have time, which I don't think we will, we'll talk about them. But these rocks are naturally fractured. Here's an example. This is this is an outcrop of the actual reservoir about 2 kilometers away. And the reason that this appears is because this whole formation actually kind of rotated at some time in geologic past. And part of it is out of the ground and part of it is in the ground. Now, you know they're exaggerating because of erosion, but we know from this and from measurements that we've done in situ that there are substantial natural fractures present. So here is a through-bed FMI. I don't know whether, are you familiar with FMI, information microimaging? So you guys have had it. You can see it's not necessarily quite as good quality as a larger diameter tool, but it's really not bad. And to process that information, and of course this is 4,500 feet, but there are substantial natural fractures that are present in this reservoir. And what is even more interesting is the natural fractures that are being detected by the sonic tool. And these are not, the ones that I'm interested in are not detected by low frequency sonic signals. They're detected by low frequency events at some distance from the wellbore. So processing the whole waveform of the sonic log that was run in this well, Schlumberger was able to detect reflectors that were 30 to 50 feet away from the wellbore that we feel are probably significant fractures that are causing this reflection. So the reservoir characterization, involves, a lot of measurements, but particularly looking for temperature and natural fractures. Of course, stress is also important. And we did a lot of measurements on stress. We tried a lot of defits, a lot of extended leak-off tests, and we were met with a lot of failures of packers. And so basically the packer elements that would isolate the injection zone just could not handle the temperatures that we were at, and so those would fail. Now luckily, in many of these cases, we could just pump down the casing and still fracture this well because the casing was strong enough. But this is something that is going to be a real challenge in the future. And so we do the same thing that we do in the oil patch. We run a diagnostic fracture injection test. This is the purists in the oil industry don't necessarily like what we did here, but we tried to optimize and maximize the amount of information that we got from this one particular defect test. And this was a test that was done at the toe of this inclined well. Okay, there were 200 feet of open hole section, and we set a packer. The packer failed, but it didn't matter, okay, because we could just pump down the casing and still inflate this open hole section and break it down. And so we first started off with a very low rate, half a barrel a minute. And this low rate is kind of important from a geothermal perspective because people sometimes believe that if you pump in a low rate, you can cause shearing of these natural fractures and you can cause asperities to override each other and create self-propping. We didn't see too much evidence of that. We saw a fracture that just gradually, opened up. That the fact that there's no breakdown, there's a fracture already there, and shut it in, not that much going on. And then the second cycle, we pumped it 5 barrels a minute for 2.5 minutes, shut it in for about 20 hours or so that we could do a G function analysis, conventional analysis that you would do in the oil patch. And then after that, we do flowback. Because our premise, and it wasn't our idea, this idea came about from people from Syntec, and Shell has followed up on it, is that this takes me 20 odd hours, and that's lucky. Okay, this granite permeability, it's like 30 microdarcies. It's much bigger than I thought it was, and that's probably because of the natural fractures. But still, I don't want to wait 24 hours with equipment sitting on location costing me $100,000 a day. So the premise is you do a flowback analysis, and so basically what we did is as soon as we stopped pumping, we flowed back for 30 seconds, shut in for 3 minutes, flowed back for 30 seconds, shut in for 3 minutes, et cetera, and walked it all the way down. And then did a plot of some sort of stabilized reciprocal rate normalized pressure and versus an equivalent time, an Agarwal type equivalent time. And man, there's a fantastic inflection that shows up on this that's very, very similar to what we get on the G function. And so this is something I'm really pressing for, that we should be investigating different ways of measuring in situ stresses that don't require these long shut-ins. I think you can still get permeability, and I'm in the interest of time. I'm going to have to skip these two, I think. So what's the bottom line? The bottom line is starting in January. We've got this one well drilled. Starting in January, we've got to frack that well, and we've picked fracks, hydraulic fracturing, and that's what most people have done. You can see these statistics in these projects. The blue is hydraulic fracturing. People have tried acidizing. People have tried thermal stimulation. Actually, thermal stimulation will work, but it takes a long time, and you got to pump a lot of fluid. We had one success in Idaho, but it took 3 years and about 3 billion gallons of fluid. And the fluid was reinjected anyways. So we're going to stimulate. A lot of these other ones come from Europe, where there are bans on hydraulic fracturing, and there are not the opportunities to do the fracturing because of environmental considerations and concerns about seismicity. And actually, so my 40 minutes is up. Okay, so I'll finish in 5 minutes.
You can take more time.
Well, you should never give me an offer like that.
I think the students will complain. That's okay.
Yeah, you get nervous when the faculty start to complain. So here's Fenton Hill, and you can see some of the fractures that developed, but there's just no communication between these two wells. This one, Rosemount in Wales, was interesting because it grew downwards, and they think that there might have been some shear fracture. So that's another reason for not drilling the second well before you know what's going on. I hope we don't have to drill our second well below. I think we're going to drill upwards. These are much more conventional, looking like radial fractures, and this is from Germany. And this one is from Basel in Switzerland. And Basel had a significant seismic event when they were actually pumping this treatment. And actually, it brought an end to the job. There were 3,600 events. One of them was over magnitude 2. But the New York Times appreciated that magnitude 2 earthquake. And you can see from the seismicity that you've got a very, very classic situation that's going here. You probably drew this fracture. And this is a wing crack, okay? And this wing crack is probably aligning with the principal stresses, okay? So beautiful. But there was sliding that occurred on here and a substantial release of energy that brought the job to the end. And that's why seismic monitoring and consciousness and stakeholder interaction is so really important in these. And we hope to find out, what do these fractures look like? Because as I said, I don't think you're going to break the matrix. I think you're going to follow some of these natural fractures. You get something like this, you get something like this, something like this. We'll find out. And it's a real challenge. And the reason it becomes a real challenge is that the recent information in the oil patch from some of the big hydraulic fracturing experiments that have been done in the Permian and elsewhere in Eagle Ford is that there's a tendency for people now to believe that certainly in the oil patch, you're getting very linear features like what you're seeing here, and I can't lie. I mean, that's what I'm seeing too, and it's ignoring the natural fractures that are and the fabric of the rock that is present. Of course, we can come up with many reasons for that, and maybe we'll just skip through here and just get to the bottom line of what's going to happen in the next little while. So we will do a stimulation. It'll probably be January or February. I mean, you wouldn't want to do it in the summer. Just like a cement job, right? If they taught you that you only do cementing at night, that's not quite true. January, February, and this is the treatment that was pumped in Benton Hill. And slick water, 50 barrels a minute, 6 million gallons, and some calcium carbonate for diversion. Nothing substantially different than what we are going to do now. But if we will opt to do 3 fracks, 2 slick water fracks, and a high viscosity fluid. Finding a high viscosity fluid that will tolerate this temperature is a bit challenging. Schlumberger had a fluid called Sapphire that they pumped once in India. And we think, even though Schlumberger has solar fracturing operations delivered, we think we'll have access to fluids like this. They are just polyacrylamides, fundamentally, just like a high viscosity friction reduction treatment. And so that'll be something. But these are the technology areas that if you want to look at geothermal in your research, it's cementing technology. These are high temperature operations, and think about what happens to casing in these, okay? Suppose I pumped a frac job and I was pumping 60-degree Fahrenheit water into a reservoir that was 500 degrees centigrade. Okay, your casing is going to really try to shrink, particularly if you have a bad cement job. And if you look at those calculations, for a 10,000-foot well, and you assume that there was no cement bond at all, it's like a shrinkage of 20, 25 feet. It's not inches, it's feet. It's substantial. And so casing design and cementing design. The other thing about cementing design in geothermal is just like you sometimes have it as in annuli in the oil field, where the fluid in the annuli heats up and it causes the internal casing to burst. Okay, and that's the biggest risk of pipe behind cementing. We're less worried about, to collapse. We're less worried about burst in these geothermal wells than often we are about collapse. That the fluid, if you've got a void in the cement and you've got water in there, and you will have water from the cement job, because there's usually a high water cement ratio and a lot of retarder because the temperature is so high, that if that water starts to expand, it's pushing in on the casing. And so often in geothermal, you worry more about the collapse than you do about burst. And in fact, what you try and do in the upper sections of the well is you want your intermediate string to burst before your production string collapses. And so it's casing design, cementing, and then stimulation. I mean, all of these are pretty straightforward. But here's the bottom line, and here's the last slide, is that what we're trying to accomplish here, that this is not a commercial project. This is a federally funded research project to develop technologies. And there are 4 C's that I think about when I talk about this. I think about connectivity. I think about joining these 2 wells. Can I do that? Okay, I don't know. What happens if I drill a second well and I find I don't have an intersection? That's tough, right? You go back in and you repump the first. You try and pump them both together. We'll cross that bridge when we get there, if we get there. Then the second step is conductivity. You have these fractures. They have to be conductive enough that you can flow large volumes of fluid through them over substantial periods of time. And that could be proppant, okay? But think about proppant. First of all, you can't use sand. You know why you can't use sand? It'll dissolve. At these temperatures, the silica will go away, okay? And so we've tested bauxite. It seems to work, although bauxite has eventually degraded too, and maybe you can see clay binder coming out of it. Or there's conversion of some of the aluminum. There's some formation of clay minerals. Intermediate strength proppant. Maybe the solution, and maybe rough proppant. Okay, because the last thing that you want in these is flowback or motion of sand, so that you're producing sand. Because think about what happens at the surface. I'm taking that hot fluid and I'm running it through a power plant, and the last thing I want is to have to call on some of your professors here to do a post-mortem on why I cut out some pipes. And so conductivity, conformance is a huge issue. Okay, we know conformance in the oil patch, right? You think about you're doing a water flood. You want to make sure that everything is equally treated in a line drive, for example. Here it's the same thing. Think about this. You've got a well like this, and you've got fractures all along the length of the well. Where does that fluid want to go? I'm pumping it down this well. It wants to go into the first crack. Okay, now what happens in that fracture? Oh, I'm pumping cold water. So what happens when I pump cold water? It cools down the formation. What happens when I cool down the formation? Believe it or not, the formation shrinks. And as the formation shrinks, that fracture becomes wider. As that fracture becomes wider, you've got a cubic relationship between conductivity and based on conductivity and fracture width. And so more and more fluid is going to want to go in there. And so conformance And mechanically controlling and having equal amounts of fluid going in each one of these over 30 years. I mean, that's the difference. That's the other difference in geothermal, is that you have to count on these plants being around for 20 to 30 years, not returning your investment in 5 years and selling it to somebody. And then the final thing is conversion. How much of this heat can be converted to electricity, and am I going to thermally deplete these reservoirs before time? So, you know, fantastic, challenging reservoir project that's really taking a lot of information from stuff that you're working on right here now. And that's about all I got. I'll try and answer any questions. Yes, sir.
Thanks for your great presentation. I really enjoyed. And my question is, you said that all those geothermal positions that near the area that which has active activities like earthquake things, that then they will generate the thermal underground. So I have one concern is that since the activity will move the underground, so is the casing will survive from those activities? Because otherwise that you have to fix it, and then the well has to stop production or injection.
Yeah. I mean, you know, this seismic activity has any number of implications. You know, the casing implication is real. Okay, if you have a fault or a significant pre-existing fracture that you mobilize, it can cut pipe, and there's really nothing you can do about it. Okay, and this is a case, you know, when you combat Mother Nature, in this case, Mother Nature always wins. Okay, I can put in dual strings of cemented casing. I'm still gonna fail that. So the key to this is geologic reconnaissance and having evidence that, to the best of your knowledge, there are no significant faults that are present in the area. And so you can imagine that, as this gentleman has pointed out, if I have a fault and I put fluid in that fault, what happens is that I reduce the effective stress, and reducing the effective stress reduces the effective normal stress, reduces the friction, and the frictional reduction causes this to slide, and I can lose my pipe, and I can't access below that. And so the question is, where does it happen? You know, can I remediate it? Do I have to patch it? Just like in the oil patch when this happens. More important for us is that if there's a significant earthquake, it's like one of those, I don't know whether they have Frankenstein movies in China, but you know, Frankenstein was a guy that was invented by a German doctor, and he has a bolt through his neck and stuff like that. And the villagers didn't like this. And one day the villagers came out with pitchforks and torches, and they wanted to drive the doctor out of town. And so if we have an event like that, really, it's not in the public's best interest, and we probably would have to look to another site. And that's why we've spent, you know, a lot of effort, you know, doing reconnaissance and trying to make sure that there aren't these significant faults that are there. We don't really know, but from the geologic perspective, we think this is probably one of the ideal places. And candidly, this is an important question. It's one of the things that is going to govern the placement of these geothermal systems. You know, I said you could go across the whole country. Is that true? I mean, probably it's going to be difficult to put one near a major metropolitan area no matter what. Even if there is a low risk of seismicity, people are still going to worry. And so, you know, everything we do has to be tempered with reality. But that's a really good question.
Yeah, because that you need to trade off, because you have more activity, because the temperature is not, it will not be easily depleted summarily. And but if you go far away from that, you don't have the risk about the case failure. Then that's the temperature is low.
Yeah. You know, in our situation, though, we're counting on the fact that it's a conductive thermal regime where there probably won't be too many significant fractures or faults that are carrying fluid to the surface in high temperature areas. And that's what we're hoping is going to prove out to be, you know, one of the reasons that will make it viable at this location.
I have many questions.
I was waiting.
The defit test you conducted,
Yes.
and you said that you did this kind of a step-rate test, right? And you said you could estimate the probability, so you didn't go into pseudo-radial flow, just, you could just use.
The defect went into pseudo-radial.
Oh, it did go
The
into-
defect, we took into pseudo-radial flow.
Okay.
And I can't remember about the flowback tests,
Okay.
how they went about estimating variability. But yeah, we probably could have waited a little longer.
No, I think my question
You know,
was,
but it was getting
yeah,
to-
my question was this step-rate test you did, and if you could come up with, I mean, is it like a different way of estimating the probability which oil industry could use? I mean, that was my question.
And I'm trying to remember what the postdoc did.
Okay.
You know, but I'm happy to send you his paper
Okay.
if it's of interest. But you know, we have to do something different. I mean, these things, these regular defect tests are taking so long that people are hesitating to do them. And you know, these flowback you can do in a couple of hours.
And then the second question was, when you drill the second well, would you frack it?
If we don't have, okay, there's two answers to that question. The first answer is if we do not have reasonable connection with the first well, I will consider going in and fracking specific zones at the toe of the second well to try and encourage connection with the fractures I created previously. Through the life of the project, we may actually even do some stimulation from the second well, even if we don't think we're going to communicate with the first well. What this sort of depends on is the allocation of research contracts that we have. And if somebody needs a well and they don't need communication, that maybe we'll give them a portion of that second well to try out something. For example, we don't have sliding sleeves in this first well because we're running 7-inch casing. Right? Sliding sleeves, you know, typically have been built for 5-inch casing. And we're running 7-inch casing because you need this bigger hole to get all this water to come through. And so we have a research project to build for one of the vendors to come up with sliding sleeves for 7-inch casing. So we might frack that second well. We'll run sliding. We'll have an open hole section. We'll have something where we have sliding sleeves and then something where we have casing perf. So we may frack strategically the second well. But if we don't have connection, then we definitely frack the second well.
Well, thank you so much, John, for your presentation. I am wondering, instead of fracture, can we combine these wells by drilling?
Okay, there's a company called Ever,
Okay.
and Ever is a Canadian company, and they have been drilling in sedimentary basins where they've been drilling 2 horizontal wells and interconnecting those horizontal wells and just circulating. So it's a closed loop. It's a closed loop system. And so the challenge with these closed loop systems is, do you have enough surface area? And you know, you have to stimulate along the length of these wells and whatever. Ever has successfully joined these 2 wells, and now actually they're talking about pinning drilling, where they're drilling, like, believe, you know, what used to be coal bed methane, and drilling multiple wells and connecting them. And so I'm optimistic. I'll just wait and see. If it's just this one well like this, no way, right? You just will not have enough surface area to have conductive heat transfer. But if you can frack it and maybe drill multiple wells, I'm you know, we'll wait. Hey, well, you've got the analytical models, you told me. You should be telling me the answer to that question.
Yeah, we have some analytical models,
Yeah.
different well configuration, actually, published in the Reservoir event.
And so I'm optimistic.
Thank you.
So I've got a question. So what's beyond the forge?
Well, I think retirement. Well, okay, so we are funded on this project through 2024. We have, you know, the DOE recognizes that there's a lot to do, and we'll probably get an extension with additional and more than a no-cost extension through 2026, I think. And we have favorable congressional representation that's pushing for 7 more years, and that, that's what so much of this takes. I mean, they don't let me talk to those guys, but our state and federal representatives and other federal representatives think this is, is good for the country, not just because of geothermal, but because of some of the supplementary and ancillary research and technology transfer from the oil industry. So, to answer your question, I think that these problems aren't going to be solved by 2024. I mean, coming up with a system that is commercially viable, it'll take a decade to get that sorted out, and then another decade to build a plant somewhere. So I think that commercialization, long-term circulation experiments, where you're pumping fluid to see how is this gonna thermally deplete in 2 weeks? Yeah, I mean, the numerical people tell me it's fine, and so we'll wait and see, and I trust them. What else? We'd like to drill another well to intersect the fractures, so like the HFTS, where we go in between the two and just see what these fractures look like. So there's any amount of research that could be proposed. Oh, plus testing of surface equipment, power plants, and some of these new generation organic Rankine cycle power plants are just unbelievable. That they can make electricity at 80 degrees centigrade. And
I heard it was 60.
Well, I didn't realize that. That's fantastic. Actually, I did another proposal about draining a mine. Okay, this was a plant mine in Arizona, where water was coming in at 180 degrees Fahrenheit and 1,400 gallons a minute, and just put one of those power plants down there and pump the water out of the mine. So really, we get back to some classical chemical engineering that is really going to be valuable at some time.
What do you think about the geothermal heat pump?
Oh, I'm bipolar, right? I mean, I like this high temperature stuff and I like the low temperature stuff. I think that if we really want to make a difference and you want to make an immediate difference, the low-hanging fruit is ground source heat pumps. Okay, and basically all that is putting a field of well bores down to a few hundred feet, and you put PVC pipes in, and you circulate some sort of heat exchange fluid, maybe just water, maybe sometimes glycol, food grade glycol, and you run this to a heat pump. And so the heat pump is just like an air conditioner, okay? And that as you expand and compress fluids, they pick up and heat, and they give off heat. And you can use these for heating and cooling buildings. And actually, we put in one at the University of Utah. There's Colorado Mesa College, hasn't turned on a boiler in 10 years. There's real opportunities. And even in Oklahoma, because you can use them for cooling as well as heating. And your cooling load is what, 3 days a year? Or your heating load is 3 days a year, and your cooling load is the rest. So yeah, I think it's a wonderful thing. And if you guys get sidetracked into that, I think it's really something of societal benefit.
Thank you, John.
I just have, this is completely like geology ignorance talking about my part, but like there's a lot of special characteristics. It seems like with the site that you guys managed to find here, just from geology and its distance. I mean, how much of that actually exists in the U.S.? I mean, that's a good question. I mean, in some sense, it seems interesting that we have all this. We're putting in all this like rural power supply, infrastructure to service wind farms and things like that. So in some weird sense, we may be bringing the expensive transmission lines to these places already. But I don't know, just a general feeling for how many of these sites actually exist.
It's a realistic question, but it's not necessarily the geology that's going to govern. It's the last thing you mentioned is putting in transmission lines that is really going to govern where these things can go. I showed a map, I don't know whether you were here at the time.
No, I saw it, yeah.
And, you know, if you drill deep enough, you can find temperature. And actually Cornell University, they're gonna do what's called a closed loop system. And Huey is funding for them to drill down 10,000 feet and use this for heating and cooling the university. And that's in granite, it's in the northeastern United States. Fairly seismically benign, but seismicity is going, in my mind, is going to what govern this ahead of the specific geologic regime. And there are sites, but you're always surprised. Most of you folks aren't from the United States, but well, I'm guessing. The biggest earthquake in the United States, it wasn't in San Francisco, it wasn't in Alaska, it wasn't in Seattle. One day it might be in Salt Lake City, but we'll see. It was in Missouri. Okay, it was in the central part of the United States, in a cratonic environment. Cratonic means, you know, flat, passive sedimentary regime without much tectonics. And so site exploration, site characterization, particularly for seismicity, is going to be the key answer to that question. And so I didn't answer. I guess I don't know.
Yeah, no, I was kind of just, I guess, wondering about field research. I think I would be right, like, you know, the downs, you can't put the zero VC because like everybody will freak out.
And then transmission becomes an issue.
Yeah, absolutely.
And so, I mean, there are other challenges, and that's why I like some of the lower temperature applications potentially, that an improvement of you know, I'm not trying to talk myself out of a job, because I think there's value to this high temperature because it's so much more efficient. But there's so many new developments on these electrical conversion devices that wouldn't be using lower temperature fluids with much less risk. And you don't even have to inject. These closed loop systems, you know, they're closed. You're not injecting fluid into the reservoir. So that's, I think, a real advantage of those. The other thing is old oil fields. I don't know if you have any idea how many orphaned and abandoned wells there are in the United States. I mean,
2 million.
Is it 2 million?
Yes.
Wow. And of the ones in Oklahoma,
600,000.
yeah, and of those, how many are just filled with like 3 feet of bed?
No, I mean, many of the wells are not properly plugged, if that's what you're saying.
And so what people are looking at is before abandoning these wells, if you have enough moderate temperature water production, to put one of these plants on it, even if it's a skid mounted unit, and try and generate electricity or direct heat. I don't know. I mean, the people are looking at it. There's a lot of interest in looking at it. We're looking at it in California because there's because the oil industry is locked out of California these days, and there are, I forget how many orphan wells in California, but it's a lot, and a lot of steam wells offset steam injection. So potentially the oil field offers some opportunities.
What about like, I mean, this idea which is that existing oil fields which are very hot, is it possible you could circulate water through it as a geothermal energy source?
Absolutely. Absolutely.
Like, what's the one in Louisiana, which is a shell field in Louisiana, and Texas, which is on the border, basically, Texas, Louisiana.
Not really.
No, Bossier is hot too, but right next to it, which is the shell play, which is.
Oh, Haynesville.
Haynesville.
Yeah. In Haynesville, the temperature is 350.
350, exactly.
And so, hey, why not? Now, the other interesting thing is that some of these new power plant devices can handle oil and water together. You know, you don't get much thermal benefit from the oil because of the specific heat. But if you're co-producing water with these and hot water, you can run the oil and water together through the same system, even if there's carried over oil.
Why is the cyclicity not tried for geothermal in the sense half and puff, where you inject and produce, inject and produce, inject and produce, and you have certain residence time in the well, basically? Why is that not practical?
I guess I don't know the answer to that, other than I don't know the answer to that, because it offers the same advantages and disadvantages. You've got parasitic loads to pump fluid in, which you've got in both cases, And in each case, you can rely on buoyancy to bring your fluids to the surface. So maybe there is some rationale for huff and puff. Well, where I've looked at huff and puff is being in conjunction with solar geothermal. That you use the solar in the day to heat up the water and inject the water, and then produce it back at night. And I just can't talk anybody into fucking it.
Well, that requires single wellbore, right?
Well, you can, I think there are different configurations that you could be injecting in one, for what I talked about, you could have a cold water injector and you could have a hot water producer. Or, let's see, a cold water producer comes up to the solar system, you inject it back into a hot well. And if the permeability is high enough, you can develop some sort of circulation system to another ring of producers. But maybe it's just.
No, I don't know.
I think it's worth looking at. And yes, sir.
Thank you, Professor, for such an excellent presentation. So I noticed that you come up with some criteria about the finding the site, and one of this is the result should be low permittivity. Why do you want some low permittivity result?
Because you want the fluid to stay in the fracture systems. Okay, you don't want the fluid to be moving deep out into the reservoir or losing fluid. If you have a lot of fluid loss in a higher permeability formation, and that's not a good answer to that question. You want something that is relatively impermeable because you want to concentrate the fluid on an optimal path going through the fracture system that you create. Yeah, I know that's not a very good answer. I got to think that one through.
Are there hot formations with permeability?
Yes, there are. And actually, people have looked at what they call sedimentary reservoirs, and extracting the heat. I was just trying to think why in our particular case. And why in our particular case is because the DOE said that's what they wanted. But that's not a very good technical answer, is it? I should be able to do better than that after this time. And I think it's just so that you can ensure that you don't have short circuiting. Okay. Here's suppose I have a high permeability formation, and I can use one of these sedimentary reservoirs, and I don't even have to frac. But suppose I do need to frac, and I've got fractures that are this far apart. Am I going to have fluid moving from one fracture system to another fracture system and short circuiting? So I pump fluid in here. It doesn't go through the fracture system. It just goes through the formation. It goes into this one. This is a big risk in this no matter what. But I think it's exaggerated if you have a permeable matrix where fluid can move laterally from one fracture system to another. I think that I talked myself into that answer.
Thank you.
More questions? You have one, Glenn?
Yes, sir.
Sure.
Yes, sir. I have a question about, you mentioned that the place you select have a lower risk of earthquake.
Yes.
So can you give some reason as why these sites have a lower risk of earthquake?
I'm not a seismologist, but I think that there's been a substantial amount of stress relief that's existed in the past in this particular geologic environment. That this is in what's called the basin and range part of the United States, where the crust is actually pulling apart or moving apart. So one of the things that I'm thinking is that you've had stress relief at some time in the geologic past, and there's not an accumulation of stress. So imagine if you're in a compressional regime, okay, where two plates are coming together like this. You're pushing two plates coming. You're building it. You're progressively increasing the strain energy that's built into that location. Whereas we're talking about this thing where the plates are we're moving apart, and you're progressively reducing the amount of native strain energy that's present. Secondly, in this particular reservoir, there's not a great deal of indication of potential fracture, not faults and fractures that we have present. And you know, the reason we kind of know that is that this has been explored for geothermal work for like 40 years. So we're lucky that there's been a lot of penetrations where people have mapped and haven't found substantial natural faults. So lack of faults, and probably I'm speculating because of the tectonic regime that this area is in.
Okay, so the natural earthquake, the risk is very low, but if you introduce more fluids and more fracture in this reservoir, the earthquake risk will increase.
Yeah. So it's different than injecting into the Arbuckle. Okay, so you know, in Oklahoma where you've done your injections, it's been in the Arbuckle formation immediately above the basement, the granite. I think it's a granitic basin. And there are faults in that basin, and you're injecting billions and billions of gallons of water. So what we're planning on doing is we're going to pump a number of small hydraulic fractures. And then we have a closed loop system, effectively closed loop. We're going to have a little fluid loss. We're not accumulating volume in the system, and that's one of the advantages of this. You know, the closed loop is even more so, that you don't know fluid in the formation, but we'll try and keep the amount of the tally of net positive fluid down to a minimum.
Thank you.
All right, if there are no more questions, let's thank our speaker.
Thank you.
Meeting you.
Hey,
Yes.
yes.
Looks like you found your luggage.
Yeah, I did.
Oh,
thanks.
Thank you.
It was a really pleasant day.
Excellent presentation. I really enjoyed it. Very nice. This is such a research-rich area.
It's once in a while. Once a research.
Fantastic.
Thank you.
This is what we die for. Maybe live for. I should say.
Thank you. Thank you.